Welcome to my channel SK Vidyayan physics classes. I shall discuss about Zener diode. Now, regarding the fabrication or construction of Zener diode, the P side and N side of the junction are heavily doped. Doping is very high, heavily doped. Now, what is the advantage of heavily doping? Now, due to the heavy doping, the thickness of the junction or width of the depletion layer is very small. There is an expression for width of depletion layer x equal to 2 epsilon Na plus Nd by E Na Nd Vb to the power 1 by 2. This is unbiased junction. Unbiased. Epsilon is the permittivity of either germanium or silicon out of which P and N are developed. Na acceptor density, Nd donor density, E charge of electron, Vb is the barrier potential. For germanium 0.3 volt, silicon 0.7 volt. Now because of this term here Na, Nd are multiplied, so this is very large, as a result of which x becomes small. Now if you consider a biasing voltage across the junction, say to be V biasing voltage, then width becomes 2 epsilon Na plus Nd by charge of electron Na Nd Vb minus V to the power half. This is due to biasing. Now, this biasing voltage may be positive, that is forward biasing, or may be negative, reverse biasing. Say P is connected to positive terminal to battery, N is negative terminal, then it becomes forward biased. Now, because of the forward biasing, the width of the depletion layer becomes less. Now, if we reverse bias, then V becomes plus V, then width of the depletion layer slightly increases. So whatever it is, the thickness of the depletion layer or thickness of the junction is very small in case of Zener diode due to high concentration of or heavily doping of the P and N section. Now, since the thickness is very small, intensity across the junction is potential difference by thickness. Intensity becomes very large. So what is the advantage of making intensity to be very large in case of Zener diode, which is due to decrease of width of the junction? Now let us analyze. Here I am enlarging. Say consider this is the depletion layer and this is the thickness of depletion layer. Now this layer is depleter of the free charges and there are only immobile ions. Now what happens? If you apply a potential difference, say reverse biasing, P is negative, N is positive, what happens? Since there will be some electrons, even if the free charges are depleted, Now there will be some electrons which is due to the thermal effect, they will be accelerated, they will pass on to the n side, constituting small current. And this current is due to minority charge carriers and reverse current. So what happens if you go on gradually increasing the potential, say go on increasing the potential, intensity of electric field grows, builds up. Now this is the 0 volt voltage potential, current is taken along y-axis in milliampere. This is the reverse biasing voltage taken along negative x-axis, and forward biasing voltage taken along positive x-axis. This is how the current varies with potential very small variation. Now for Zener diode, this variation occurs till a potential is reached where the current becomes very large, increases very sharply, and this voltage is called Zener breakdown voltage, or it is Vz. Now again I am telling, because of the minute charge carriers, electrons in p region, which moves towards the n side, because of the electric field is from n to p due to reverse biasing, current flows because these electrons are now swept out by the positive terminal. Now as you go on increasing potential, then the current variation takes place very small amount, but when the potential reaches the breakdown voltage, then the current increases very sharply. Very large amount of current flows to the junction, and the electrons are swept out by the positive terminal of the battery. Now why this thing occurs? You can compare this breakdown as avalanche breakdown, as avalanche in landslide. Snow gradually comes down the mountain, and after going through some distance, very small distance, it attains such a enormous large amount of snow comes down, in avalanche takes place, very enormous mass of snow comes down. Similarly, why this happen? Now the width is very small, intensity is very large, that is about 2 into 10 to the power 7 volts per meter. At this value of intensity, what happens? Electrons from the covalent bond are pulled out, that is covalent bonds rupture. Because of the rupture of the covalent bonds, large amount of electrons are produced and they flow towards the n region, finally to the positive terminal of the battery. Now this intensity is achieved when the voltage across the junction is nearly 6 volts, and the rupture mechanism, because of the rupture of the covalent bonds, electrons are produced, and this breakdown is called Zener breakdown, and Zener current increases very sharply. At this region, the resistance falls very sharply, and this is the advantage of Zener, for which we can use it as a voltage regulator, because the current increases at a constant voltage Vz. Now this is the Zener breakdown, and Zener breakdown is reversible. The moment you switch off the electric field, the system comes back to original configuration. Now another mechanism for producing large amount of current is there, that is avalanche breakdown. In avalanche breakdown, the doping of P region, N region is light, is small, as a result of which the width of the depletion layer is comparatively large. Now, under such circumstances, the electrons, the minority carriers from P region moves towards N region, and while in motion it gains energy because it is wide, the depletion width is wide. It gains energy and due to collision, knocks out electrons, producing more and more electrons, and the process builds up, continues, and suddenly there is a large amount of electrons moving towards the N region and finally swept out by the positive terminal of the battery. But this avalanche breakdown, because of the comparatively larger width of the depletion layer, takes place at a larger voltage. If you compare the avalanche breakdown in the same graph, there will be current, large amount of current varies in an enormous manner, but at comparatively higher voltage, that is say VA, and out of these two graphs, this is for avalanche, this is for Zener breakdown. Zener breakdown is reversible, avalanche breakdown is irreversible. Now, out of this, avalanche takes place because of collisions of electrons, Zener because of the rupture of covalent bonds due to high or intense electric field across the junction. Now, whatever be, whether it is avalanche breakdown or Zener breakdown, the current increases so sharply that unless we control the amount of current passing through junction, there will be thermal breakdown or thermal runaway of the device. For that reason, with an Zener diode, we connect a series resistor. This is the symbol of Zener diode. Zener diode is always connected in reverse bias, that is operates under reverse bias condition. Now, this is in a series resistor. Now, if you connect a series resistor with Zener diode, that can regulate the current so that Zener diode is not damaged. Now, we shall come to voltage regulation of Zener diode, by Zener diode. Now let us analyze a circuit. Here, this is the unregulated voltage taken between the terminals A and B. Unregulated voltage. It may be from the output of rectifier, and this is a series resistor, say RS, and here we have a Zener diode, and like this it is connected, and there is a load resistor RL, across which the regulated voltage will be obtained. Say at the terminal C and D, it is RL, it is Zener. Now, Zener diode is operated under reverse biased condition. This is the N section, this is the P section, series resistor and RL. Say it is Vz is the Zener voltage at which Zener breakdown occurs, and this is the plus or minus. Now, what happens? Because of the unregulated power supply, unregulated voltage, a current say flows in RS say IS. Now, since it is not regulated one, it is not fixed one, there may be a fluctuation of voltage across RS, that is series resistor. This fluctuating voltage produces fluctuation of current, and increase of current passes through the Zener diode, maintaining a constant potential across RL. Similarly, if the current decreases within a particular limit, then the voltage also is maintained, because the decrease in current is also not affected, does not affect the potential across the Zener. It maintains a particular potential equal to Vz. So what is the very important relations? Very important relations say if Vi is the input voltage, then Is should be equal to Vi minus Vz by Rs. That is R equal to V by I. So current Is into resistance in series Rs equal to Vi minus Vz. Second relation, if this is the current through the Zener equal to Iz, load current is IL, then Is is equal to Iz plus IL. Third relation, that is Vz equal to IL RL. If we understand these three relations, then we can solve numericals. Now let us consider a problem that is, say, like this. This is 6 volt, and this unregulated voltage Vi, say 10 volt, and this is 1 kilo ohm, and this is say RL 10 kilo ohm. You have to find out the value of Iz. We have to find out value of Iz. Find Iz. How to solve it? Now, the current Is through the series resistor, that is 1 kilo ohm, as you know, R equal to V by I. The current Is equal to the net potential is 6 volt, here 10 volt, 10 minus 6, 4 volt, into series resistance 1 kilo ohm. This is equal to 4 milliampere. Now, the current in RL, this is equal to IL, which is equal to, this is equal to 6 volt by RL is 10 kilo ohm, that is 0.6 milliampere. So that Is equal to Iz plus IL, and Iz equal to 4 minus 0.6 is 3.4 milliampere. One should, while solving this problem, before that one should check that whether the open circuit voltage across RL is greater than 6 volt or less than 6 volt. That is, open circuit means you take out mentally, you take away Zener diode. Now the potential across RL, say VO, equal to 10 volt. Total resistance is 1 kilo ohm, 11 kilo ohm, 11 kilo ohm. This is the current through RL, and potential across RL is 10 kilo ohm. So it is equal to 100 by 11 kilo ohm cancels. That is 9.09 volt. which is definite. In the absence of the Zener diode, there will be a potential of 9.09 volt. Now we are regulating that potential to a value equal to 6 volt. So very important point is that if you allow the current to increase, then the incremental current passes through the Zener diode, because at this point a Zener breakdown, the resistance becomes very small, allows current to pass through, maintaining a constant potential. I hope the discussion will be very much helpful for students appearing NEET and JEE. Thank you.